this tutorial we present an example using the ADC, touch and graphics display in the emWin environment, which is integrated in Keil MDK Professional. Let's create a new project in Keil MDK, selecting the microcontroller STM32F7 NGHX. The Manage Runtime Environment window appears and we select the board 746. Then in the Board Support tab we check the emWin LCD and the LED API. We hit Resolve and then we choose the Classic Cube framework in the device slot. Remember that using the LCD needs also the use of the SDRAM, so we check it in the slot Board Support, Drivers and then Resolve. For input device in the graphics slot, we choose Touchscreen and then Resolve. Our code will be placed in two template files that we add to the source group 1. First we shall add from the user code template device a main module for the STM32 cube. We shall add in the same group from user code template graphics the emWin GUI thread for single tasking execution model. Now we build the project and see if everything is okay. In order to use the graphics, we have to do some adjustments to the memory and the stacks. First, in the GUI-conf.c at line 56, we will modify the number of bytes available for GUI to 10,000 hexa. Then we open rtx-conf.cmc, expand the configuration wizard, and adjust the main thread stack size to more than 1000 and the total stack size to more than 4000. We also specify the clock for timer 216 MHz and the timer's thread stack size to over 1000. In the main C, we must cancel the default access share in the memory protect unit. Now we have to include the necessary headers of GUI, SDRAM, and board LED in main C. And dialog point H in GUI single thread C. We also copy the init GUI thread function prototype from here and declare it as extern in main C. Also, before the infinite loop, we have to initialize the SDRAM LED GUI thread and GUI. In the infinite loop, we shall insert a short delay necessary for the graphics thread. Now we may start to create and use the graphical objects, widgets. First we will create the main window. The parameters are a pointer to the title or just a string, a pointer to a callback function, the state flags, and the coordinates. Our LCD has 480 times 272 points, but we may use other values also. We named the window emWin and declare it as a FrameWin handle type. The callback function mechanism involves a certain formalism that is recommended by the producer and should be clear for those familiar with object-oriented programming. We name it WinCallback and construct it here starting at line 17. First we get the dimension inside the window. Then I draw a rectangle with these dimensions. We may set the colors for background. And foreground. Clear the area. Choose the font. Write strings. draw lines, etc. using the standard GUI functions. Remember to choose your preferred settings for text completion in Edit Configuration. For example, I checked, among others, symbols after two characters, which suggest the words that you are looking for. We may now build the project, load it into the Flash, and see the results. Let us use a progress bar now. We choose a name for this object, then use an instruction that creates the prog bar as a substructure of the main window. We select its position, dimension, parent, and appearance, and no extra parameters. Of course, we must declare the type of this object, a progbar handle 1. Now we may use it in the infinite loop of the GUI source file. For example, we may set a value to be indicated by the progress bar. Let us test for a constant value, let's say 35%. Compiling and loading into the Flash, we may see this progress bar with a constant value. In the following, we want to read a value from an analog input, let's say pin A0 from the board connector, which is the in0 input of the ADC1. In some previous videos we showed how to initialize the ADC using various methods. Here we will use the power of cube, but it seems that its connection with Keil MDK is not yet fully functional, so we will simply copy the code from a new cube-generated project. We first select the board, then clear the pins. Then we activate in0 for ADC1 and configure it with a proper clock. Let's choose here the discontinuous mode and no interrupts, as the speed can't be too high in this simple graphical environment. We choose a directory and a name, then we generate the code for MDK ARM v5. We open it and investigate the main file. First we copy the type definition from the handler HADC1 from the new project to the main C file of the graphics project in the beginning part. We will move it properly later. For using the ADC, we must open the RTE manager and activate it in device STM32Cube HAL. Go to the new project and copy the prototype functions for ADC1 and GPIO to the corresponding zone in the graphics project. Let us move the HADC1 type definition in this zone also for uniformity. We must initialize ADC1 and GPIO-A, which contains the input in 0, so we copy these instructions from the new project to the initialization zone of the graphics project. Now we go back to the new project and look for the body of ADC1 init function. We select the whole block, including the clock for GPIO-A. We copy it in the graphics project after the bodies of its initialization functions. However, we didn't initialize yet the GPIO-A. It may be done simply by adding the file STM32F7 MSPC, which exists in the source directory of the new file, to the source group 1 of the graphics project, and it concludes the ADC initialization. When somebody finds a simple way, please include it in the comments. We should build the graphics project and verify if it is okay. Now we may use the ADC in the usual way, like in the previous tutorials. In the infinite loop of the main C, we shall start ADC1, then poll for conversion. We read the converted value in a properly scaled variable and force it to be an unsigned 16-bit integer variable. The scale is 0.025, as the maximum value given by the ADC is 4095, so we approximate that the product to be 100. As we need this variable in the graphic dealing file, GUI single thread C, we also declare it here as an external one. Finally, we may use the converted value to be shown in the progress bar. We connect the cursor of a potentiometer to A0 and its extremities to GND and VCC, and we test. Of course, you may disable the discontinuous conversion mode and enable the continuous mode. This way, you don't need to poll for conversion, as a delay was already included for the graphics needs. Also, the ADC start could be placed before the infinite loop. Now let's introduce an YT graph, which will display the converted value as a function of time. We name the graph object, create it as a child of main window, and write the parameters: position, size, parent, and state. We shall declare it as a graph handle object. Then we choose a color for the graph background. We have to create the data object to be displayed on the graph, having as parameters the color, the maximum number of points, the pointer to the data values, and the current number of points. We also declare this object as a graph data handle 1. In order to display this object on the graph, we attach the data object to the graph object. In the infinite loop of the GUI thread, we may add now new values to the object data. Those provided by the ADC1. They will be displayed by the GUI exec instruction, which is already present in the template. We may compile, load, and test the project. We notice that the image is flickering, so we have to use a delay to facilitate the persistence of vision. The speed is now lower, but the visibility improves. Now let's use a slider to adjust the time scale. Just like before, we create the slider object, giving the name and parameters. Position, size, parent, and state. The name is declared as a slider handler. We may read the slider value in the infinite loop and add it to the delay for adjusting the time scale. Testing the project, we noticed that sometimes when we touch the screen, the application stops. To avoid this, before executing the touch function, we must test that the operating system is ready for it. This way, we do not have any such problem. Now let's use a checkbox to start and stop the graphics. Just like before, we create the checkbox object giving the name and parameters. Position, size, parent, and state. The name is declared as a checkbox handler. In the infinite loop, we check if this object is checked and in this case we allow the updating process for progbar and graph. One may add many other widgets following the documentation from Seger emWin. For example, let's introduce a radio button and then you may use it as you want. We create the radio button, specifying the parameters, position, size, parent, and state. We also specify for this widget 3 buttons and 15 points between them. The name is declared as a radio handle object. Using the widgets is very easy, especially assisted by GUI Builder, but you can't expect too much speed for such a simple half-hour made project. Much better performance may be obtained by using assembly language and EMA to write directly in the video memory.